Imagine you're holding a stone in your hand. It has no special color, it doesn't glow. There's nothing about it that draws your attention. It looks completely ordinary, just like millions of other stones on Earth. But during World War II, it was this very thing that caused two massive explosions that changed human history forever.
Strike on the scene.
The source of that immense power comes from an element hidden deep inside it: uranium. So how did humans discover uranium? Why is Iran willing to go to great lengths, even at huge economic cost, to possess it at all costs? Let's go back to the 18th century. In 1789, inside a laboratory in Berlin, a German chemist named Martin Heinrich Klaproth discovered a black mineral called pitchblende in acid, and eventually obtained a strange yellow precipitate. Although he didn't know exactly what it was, its unusual chemical properties led him to believe that it must contain a completely new element. Klaproth named it uranium, inspired by the planet Uranus, which had been discovered not long before. Holding the yellow powder in his hand, Klaproth believed he'd found pure uranium. But in reality, it was only a compound of uranium. It wasn't until 1841 that a French chemist, Eugène Melchior Peligot, noticed that this yellow powder behaved like a metallic compound, as it could react with acids to form salts. He suspected that this uranium powder might actually be a pure metal. To test his hypothesis, Peligot reacted the yellow powder with chlorine to form UCl4. In this compound, the bond between uranium and chlorine became weaker. He then introduced potassium, a metal that readily bonds with chlorine, into the mixture. As potassium pulled the chlorine toward itself, uranium was left behind on its own. Peligot obtained a small metallic-looking solid. From that point on, humanity finally realized that uranium is, in fact, a metal. Then in 1938, two German scientists, Otto Hahn and Fritz Strassmann, conducted what seemed like an unthinkable experiment. They bombarded uranium nuclei with neutrons. As a result, the uranium nucleus split in two. But it didn't stop there. When the nucleus split, it also released two new neutrons, along with a small amount of energy. These neutrons went on to strike other uranium nuclei, causing them to split as well, releasing two more neutrons in the same way. In 1939, upon observing this, Hungarian physicist Leo Szilard suddenly realized something terrifying. If a large amount of uranium were gathered in one place, a chain fission reaction could occur, releasing an enormous amount of energy. To better understand this, think of the story about the inventor of the chessboard who asked the king for a reward. 1 grain of rice for the first square, 2 on the second, 4 on the third, doubling all the way to the 64th square. At first, the amount seems small, but by the final squares, the number of grains becomes so vast it could cover the entire Earth. Uranium behaves in much the same way. When a neutron strikes a uranium atom's nucleus, it splits, releasing energy and 2 or 3 new neutrons. These new neutrons then crash into neighboring atoms. From 1 to 2, 2 to 4, 4 to 8, this process happens in mere milliseconds. Although a single uranium-235 nucleus releases about 200 mega-electron volts, MeV, when it splits, far too little to even move a grain of sand. But remember the chessboard analogy. After only around 80 steps, a chunk of uranium no bigger than an orange could release energy equivalent to 20,000 tons of TNT, enough to level an entire city. However, upon hearing Leo Szilard's hypothesis, the Danish physicist Niels Bohr raised a critical question. If natural uranium were so easily fissionable, why didn't the uranium samples in his laboratory spontaneously explode when exposed to neutrons in the surrounding environment? After a series of experiments, Bohr finally discovered that only the isotope uranium-235 could undergo fission, while uranium-238 could not. Basically, U-235 and U-238 are both forms of uranium, since their nuclei each contain the same 92 protons. The difference lies in the number of neutrons. It's like two siblings from the same family, similar in many ways, but completely different in weight and temperament. The problem is that in any given chunk of Earth you dig up, the amount of U-235 is extremely small, only about 0.7%. The rest is almost entirely U-238, making up about 99.3%. Because of this, if humans want to harness the immense energy described in Leo Szilard's hypothesis, they must find a way to extract U-235 and remove U-238 from the material they mine. Only when the concentration of U-235 increases can uranium be put to practical use. This process of increasing the proportion of U-235 is simply known as uranium enrichment. However, separating these two siblings is no easy task. Because they are chemically identical, you can't use acids or other reagents to separate them. The only way is to rely on their tiny difference in mass to distinguish between them. First, raw uranium ore is mined from the ground, then crushed and dissolved in acid. The result is a bright yellow dry powder known as yellowcake. The yellowcake is then reacted with fluorine to produce uranium hexafluoride gas. But why turn it into gas? Because in gaseous form, U-238 molecules are slightly heavier than U-235 molecules. This gas mixture is then fed into thousands of centrifuges arranged in a long cascade. These machines spin at tens of thousands of revolutions per minute, faster than the speed of sound. Under the immense centrifugal force, the heavier U-238 molecules are pushed outward toward the walls, while the lighter U-235 molecules remain concentrated near the center. However, after a single spin, one centrifuge can only increase the U-235 concentration from 0.7% to about 0.71%. That's still far too low. So after the gas completes one stage, the enriched portion is immediately fed into the next stage, and the next. Meanwhile, the U-238 rich portion is sent back to earlier stages for further processing or removed as waste. The process repeats over and over, with the uranium gas passing through hundreds or even thousands of stages. Each stage increases the concentration slightly until the desired level is finally reached. Once the uranium gas has reached the desired level of enrichment, it's then processed again to be converted back from gas into a solid form. This material is a black powder called uranium dioxide. From this point on, uranium can finally be put to use. After the black powder is compressed into small ceramic pellets, with U-235 enriched to about 3 to 5%, it's used in nuclear power plants. And just a single pellet can provide enough electricity for one household for an entire year. Looking at a larger scale, for a city with 1 million households, we would need about 1 million uranium pellets per year. That may sound like a lot, but if you stack them all together, they would take up less than 1 cubic meter of space, roughly the size of a small refrigerator. In addition, we can now operate nuclear-powered vessels. In these cases, uranium is enriched to around 20%. With just about 500 kilograms of such uranium, a vessel can run continuously for up to 25 years without needing to refuel. Finally, at the weapons level, uranium is enriched to extremely high concentrations, over 90%. At this point, only about 50 kilograms is needed. The U-235 atoms are packed closely together, and with just a small trigger, they can all undergo fission at once, releasing an enormous amount of destructive energy. Today, a number of countries around the world possess hundreds of kilograms of uranium enriched to this level. However, Iran has taken a different approach. Tehran has chosen to enrich uranium only up to about 60%. Technically, going from 60% to 90% can be done very quickly. Because of this, Iran can create what is often referred to as a virtual deterrent capability. In other words, it forces potential adversaries to think twice before launching a full-scale attack, out of concern that Iran could complete a nuclear weapon in a short period of time. But why is it faster to go from 60% to 90%? It may sound counterintuitive, but imagine it like this. You have a bag containing 1,000 marbles, of which only 7 are red and the rest are blue. In the early stage, you have to sift through tons of raw material to remove a massive number of blue marbles. But in the later stage, your mixture is already highly concentrated with red marbles. Only a small number of blue ones remain. To increase the ratio from 60% to 90%, the centrifuge only needs to remove a small amount of the remaining impurities. In other words, once you reach that 60% threshold, you've already completed about 95% of the technical journey toward weapons-grade material. But why is Iran racing to enrich uranium even at enormous economic cost? The answer lies in its extremely tense geopolitical environment. It's a region where major powers like the United States are constantly watching and competing over influence and resources. Because of that, possessing a nuclear deterrent capability is seen as a way to protect national sovereignty. Lessons from countries like Libya and Iraq suggest that powerful nations can intervene and even change regimes if they choose to, especially if those countries lack nuclear capability. Meanwhile, countries with nuclear deterrents, such as North Korea, are often viewed as far more difficult to challenge directly. And so, from a simple stone you might pick up in your backyard, scientists have learned how to turn it into something like an energy battery, something that can power an entire city, or destroy one in the blink of an eye. For some nations, the ability to enrich uranium is not just a milestone of scientific and technological achievement, but also a means of self-defense and a way to ensure energy security in an unpredictable political world.